Theorem is if a and b are two non-zero integers and a, b, GCD is d, then LCM of a, b is equal to a, b absolute over d. What it's mean? If we have two numbers and know their GCD, we can find out their LCM by this formula. We are going to prove this. As if I have two numbers, we clear this concept from an example. LCM is 2. So if their GCD is 2, if their GCD is 2, what is their LCM then? Least common multiple. What is their LCM? Their LCM, multiply these two numbers and divide with GCD, then I have 12, their LCM. We can find out there. We just want to prove this. Here two things are given. AB are non-zero. I write here, and GCD of AB is D. We know that. We suppose that its GCD is M. So actually I want to prove this, it must be equal to M. What it's mean? If greatest common divisor of 4 and 6 is 2, then 2 divides 4 and 2 divides 6. Okay, this is divisor of both number. So divisor, just like that, this is divisor of these two numbers. So divisor must divide these numbers. D divides A and D divides B. Okay, so I can write is 6 as a 2 multiply 3 and 4 as a 2 multiply 2. Here just like that. So this is divisor and this is multiple. So multiple can be written as two factors. Okay, multiple can be written as B1D. This is equation 1 and this is equation 2. Okay, so here, and you know that A1, B1 must be relative prime. Here you can see that this is A1, this is B1, 2 and 3 must be relative prime. So now we prove the conditions of LCM. We prove the conditions of M. What are the conditions of LCM? M must be greater than 0 on this LCM. M divides A and A divides M and B divides M. This is second condition. This is first, this is second. What is the third? There exists C such that A divides C, this is common multiple. So this A divides C and B divides C, then M divides C. We prove this. Okay, we prove this and we want to prove this. If we prove three conditions of LCM, that is the definition of LCM, so M must be LCM of this. Okay, for this, consider, for first condition, consider M is equal to, just we consider this expression AB over D. So as you know that here AB is greater than 0, absolute value is greater than 0, and D is also greater than 0. Therefore, their division must be greater than 0. M must be greater than 0. This is the first condition we proved. Okay, now second condition, first condition we prove this. Now what is the second condition we want to prove? A divides M and B divides M. Now again consider what I have considered, this expression. Okay, A B absolute value over D is equal to M. Okay, now plug in the value of B here. What is B? A, B1, D. And what is D? What over is D? We cancel D with D. Now which implies what happens? M is equal to AB1. What it's mean? This is multiple and these are two factors. These are two factors. Okay, this is multiple and these are two its factor. Just like that, 6 is equal to 2 multiply 3. These are two factor and this is multiple. So factor must divide multiple. What it's mean? A divides M, which implies A divides M. Okay, now again consider M is equal to AB. Plug in the value of A here. What is A? A1D and B. What is over? Over is D. So I can cancel here D with D. So what is the answer? What implies? Implies that M is equal to A1B. A1B. This is multiple. These are two factors. What it implies? This implies that B divides M. So what we concluded that A divides M and B divides M. Okay, this is the second condition. This is the second condition of LCM. Okay, what is the third condition now? Third condition, then there exists C belongs to set of integers such that A divides such that A divides C and B divides C. This is a common multiple, just like that as I take in example 24. Okay, so as you know that we take the example of 4 and 6. So 4 also divide 24 and 6 also divide 24 here. So I can write C is equal to A2. Just like that, if 4 divides 6, I can write 24. 4 multiplies 6. This is A, this is A2, this is A2. And what is this? C, B, B2. Just like that, I can write it as you know that here, if these C and C both are equal to C, which implies A2 is equal to B, B2. Okay, A2 and B, B2. Plug in the value of A here. A is equal to A1D A2 and B is equal to B1D B2. I can cancel the value of D on the both sides, so which implies, as you know that B1 did not divide A1 because A1 and B1 are relative prime here. Okay, so these are two factors, so this, if this does not divide this, so B1 divides, which implies B1 divides A2. So A2, put the value of A2, plug in the value of A2 in this equation. So put 4 in above. Okay, so what is C? C become B1 A B1T. C become A B1T. What it's mean? It's mean, now if I put the value, plug in the value of A. What is the value of A? A1D B1 into T. If these are factors, this is product. What it's mean? It's mean that these must be divide A1D B1 must divide C, as what is M? M is AB over D, as you know that. If I plug in the values of A and B here, A1B, A1D, and B is B1D, B1D over D. I can cancel D with 1D. So what is here? A1B, 1D. And you can see here this value is equal to this value. Okay, if I write here just like this B1 and DB1. Okay, I write DB1. This now this is same. That is also same. There is no difference between 3 multiply 5 and 5 multiply 3, as you know that. So what is this? This is M. It's mean 5 implies M divides C. So here I just revise this briefly. We just proved that LCM of these two numbers must be equal to this. Okay, for this we give it name M. We have to prove the three conditions of M. What are the three conditions? M must be greater than 0. For this we consider this, as we know that this is greater than 0 and D is also greater than 0. GCD of two numbers must be greater than 0. So division of these two numbers are greater than 0. For second condition, this we again consider this expression and first plug in the value of A1, then plug in the value of A1 and then value of B1. Okay, from there A divides M and B divides M. I prove this. And for the third condition, what is the third condition? Third condition is this. For this I consider if A divides C and B divides C, I consider a common multiple. Then C can be written as AA2. If this is divisor and this is multiple, this divides this, so this can be written as the product of two factors. So C can be written as product of two factors. If both this side and this side is equal to C, then these can be written as equal terms. We plug in the value of A and B from here. Okay, then I cancel D and D. As you know that B1 does not divides A1 because A1 and B1 are relative primes. So B1 must divide A2. If A2 is multiple and B1 is this is dividend and this is divisor, so this multiple can be written as two factors. Okay, I put this value in this equation. Okay, I plug in this value of A2 in this equation, A B1T. Then I again plug in the value of A here, the value of A here, A1D, B1T. As I know that it's mean this is multiple and these are its factor. This is one factor, this is another factor. So this must divide C. As I see that M is equal to A and B, if I plug in the value of A and B in this, I cancel D and D. This becomes equal to M. So M divides C. This completes our proof.